All right, folks, welcome linear algebra fans, a video on linear dependence and span. Last time we came up with the definition for a linearly independent set, one which has only a trivial relation of linear dependence. Today we'll talk about some consequences of sets that are linearly dependent, and we'll see that a linearly dependent set implies extra vectors, and we'll see sort of a methodical way to cast out those vectors. So today we'll start with a theorem rather than starting with a definition. Here's the theorem. The theorem supposes that we have a set of n vectors. Then S is linearly dependent if and only if there's some t such that u sub t is a linear combination of the other vectors. Okay, so this is a theorem that I'll let you have a look at on the worksheet. I'll go ahead and prove part of it. I'll prove the P implies Q statement. So the P statement here is suppose that S is linearly dependent, and then we want to show that one of the vectors is a linear combination of the others. Okay, well, S is linearly dependent means that there's a non-trivial relation of linear dependence on S. Now what that means is that alpha 1 u1 plus alpha 2 u2 all the way out to alpha n un is 0 for not all the alphas equal to 0. Okay, so if alpha t is the one that's not 0, then it had better be that minus alpha t ut is the sum you see here. So we can, of course, express u sub t as minus alpha 1 over alpha t u1 all the way out to minus alpha t minus 1 over alpha t ut minus 1 minus alpha t plus 1 over alpha t ut plus 1 all the way out to minus alpha n over alpha t u sub n. Okay, so we see then that our vector u sub t is a linear combination of the other vectors. Okay, so I'll let you prove the other direction. In any case, this is an if and only if statement, right? So linearly dependent if and only if one of the vectors is a linear combination of the others. Okay, so here's an example that sort of illustrates this theorem. Let's have a look at this set R, 4 vectors from R5, and let's take V to be the span of R, right? The set of all possible linear combinations. Okay, what we'll do here is come up with a strategy to describe V as efficiently as possible, sort of with the least number of vectors. Okay, and the way that we do that is by showing that R is linearly dependent and the vector v3 is a linear combination of the other ones. Okay, so in order to do that, we'll form the matrix D. This matrix D will have the vectors v1 out to v4 as columns. Okay, in doing so, reducing D to reduced row echelon form, we see that the homogeneous linear system has a solution that can be described in vector form as x4 times minus 4, 0, minus 1, 1. Okay, so we can see then that minus 4 v1 plus 0 v2 minus v3 plus v4 had better be 0. Okay, so in this case we'll express v3 as minus 4 v1 plus v4. Okay, now we're going to do something interesting here. We're going to instead define a new set. That set R prime is going to be the set of vectors v1, v2, v4. Okay, so what we'll do here is show that the span of R prime is the same as the span of R. Okay, I want to point out that that what we're showing here is an example of set equality. So the way we'll do that is in two steps, by first showing that V is a subset of V prime, and then by showing that V prime is a subset of V. So we'll start by showing that V is a subset of V prime. Okay, so let's take U to be in the set V, that is U is in the span of R. Well, then U has to be some linear combination alpha 1 V1 out to alpha 4 V4. Okay, this is just, again, the definition. U is in the span of R, right? U is a linear combination of the elements of R. Okay, but now in this case, we know that V3 can be represented by minus 4 V1 plus V4. Okay, so we see, therefore, that U can be represented as a linear combination of V1, V2, and V4, which tells us that any element U that's in the span of R is also in the span of R prime. Okay, similarly, we can show that R is a subset, that V prime is a subset of V. Okay, if U is in the set V prime, that is, U is an element of the span of R prime, then U has to be a linear combination of elements from R. Now, as it turns out, it's quite quick to write U now as a linear combination of elements from R just by setting the third coefficient equal to 0. Okay, so we see that when U is beta 1 V1 plus beta 2 V2 plus beta 4 V4, that U is also beta 1 V1 plus beta 2 V2 plus 0 V3 plus beta 4 V4, so that U is also in the span of R. Okay, so it turns out by casting out this vector V3 that's linearly dependent, we end up with the same span. Okay, so we can always do this, as it turns out, for a linearly dependent set. We can cast out vectors until we reach a linearly independent set. Okay, we can always cast out vectors from a linearly dependent set until it's linearly independent. And that linearly independent set, it turns out, will have the same span. Okay, so here's sort of a really big and messy example. We have 7 vectors from C4. Those vectors must be linearly dependent, right? We have way too many vectors to be linearly independent. So we'll go ahead and cast out vectors methodically to cook up a set that's linearly independent that, as it turns out, has the same span. Okay, we'll start by forming a matrix A containing the vectors from S as columns. Reducing that matrix to reduced row echelon form, we see that of those 7 columns, there are 3 pivot columns, so we would expect that the homogeneous linear system has 7 minus 3 equal to 4 free variables. Okay, so with those free variables, 4 free variables, x2, x5, x6, and x7, we would expect that the homogeneous linear system has a vector form of a solution that looks like this. Okay, and we know how to fill in these details. I won't go through that, but here's what you get when you set those, when you identify the free variables. So here's the solution to the homogeneous system of linear equations. Okay, now we can sort of cast out vectors methodically by setting one element to be 0 and keeping, setting one of our free variables equal to 1 and keeping the others to be 0. So for instance, we'll start by setting x2 equal to 1, x5, x6, x7 equal to 0. Okay, when we do that, returning back to our original matrix A, we can see that the relation of linear dependence is that minus 4a1 plus a2 is equal to 0. Or, in other words, a2 is 4a1. Okay, that tells us that a2 is extra. We don't need that. We can similarly set x5 equal to 1, x2, x6, and x7 all to be 0. Okay, so setting x5 equal to 1, x2, x6, and x7 equal to 0 tells us that minus 2a1 minus a3 minus 2a4 plus a5 is 0. So a5 can be written in terms of a1, a3, and a4. Okay, similarly, this tells us that a5 is extra. And when we play this game with x6 and x7, we find that a6 and a7 are also extra. Okay, and just in case I wasn't clear by these vectors a sub whatever, I mean the ith column of the matrix A, right? So we see then that each vector in our original set that corresponds to a free variable is extra. Okay, in other words, we can better express this set as a set of vectors where we've cast out all of the other ones. So this set ends up being the set A1, A3, A4. Okay, as it turns out, we end up with a set W such that W has the same span as S, and moreover, W ends up being linearly independent. Okay, this is sort of a super great characteristic that we can cast out vectors until we end up with a linearly independent set. Okay, so this always works. And when we say always, of course, there's the theorem. And the theorem is that if you have a set of vectors and W is the span of that set, and A is the row-reduced echelon form, and A is a matrix with columns from that set, if we find B as the row-reduced echelon form and identify the pivot columns of B, then those pivot columns, if we go back to the set S, is a linearly independent set with the same span. Okay, so this gives us, again, a way to cast out vectors methodically, keeping a linearly independent set that has the same span. Okay, so again here, the take-home message, for the proof, see the text, but the take-home message is that is a method for casting out extra vectors. So I'll let you work on this on the worksheet. Here's an example of 5 vectors from C4, right? Of course, 5 vectors from C4 must be linearly dependent. Okay, so in order to methodically cast out extra vectors, we'll go ahead and rewrite a matrix A that has the columns where the columns are the vectors. Okay, we can see that the row-reduced echelon form has pivots in column 1 and column 3. So what we'll do here is keep vector 1 and vector 3 from the original set, and it turns out that those 2 vectors are linearly independent with the same span. Okay, there are other possibilities too, right? This is not a unique process. Other possibilities include instead keeping the second vector and the third vector, right? Of course, if you stare at this really quickly, you can see that the second vector is exactly a scalar multiple of the first, right? So keeping the second vector and the third should be the same, and you can keep other vectors too. But our way here gives us an opportunity to sort of think about it methodically. Okay. Now, a little bit more on this set. Let's go ahead sorry, this is a new example, but let's go ahead and look at the set R of 5 vectors from C4. Again, this set is linearly dependent. Something we can definitely do is generate an element of the span of R. I'll generate an element of the span of R by taking 6 times V1 plus -7 times V2 plus V3 plus 6 times V4 plus 2 times V5. It turns out that that element of the span of R is 9, 2, 1, minus 3. Okay, so we're going to come back to this vector a little bit later. Okay. Now, of course, this set is linearly dependent, so we can apply our theorem and cast out redundant vectors to keep the same span. Okay, so again here, we would keep the first vector, we would keep the third vector, the second vector, and we would keep the fourth vector. Okay. That we're going to call that set the set P. Okay, so again, the set P is V1, V2, and V4. Now, we know that the span of P is the same as the span of R, right? That's the theorem. Since Y was in the span of R, we ought to be able to identify Y as a linear combination of elements from P. Okay, we know how to do this, right? We know how to write one vector as a linear combination of other vectors, and we know that doing that requires us to solve a certain linear system. Okay, so Y in the span of P means that Y is a linear combination of V1, V2, and V4. So we'll go ahead and have a look at the corresponding linear system. So here's the linear system where we've taken here V1, V2, V3, and V4 as the first 3 columns of the matrix. And then we've augmented by the vector Y. So reducing to row echelon form, we see that this system, alpha 1 V1 plus alpha 2 V2 plus alpha 4 V4 has a unique solution, and that solution is alpha 1 equals to 1, alpha 2 equals to -3, and alpha 4 equals to 2. Okay, and moreover, that expression is unique. Okay, so this is a pretty cool deal. Let me sort of summarize. What we've done here is come up with a set P that's smaller than R, right? P contains fewer vectors than R, but it's big enough to create any vector that's in the span of R. Okay, now, as it turns out, there are many ways to write Y as a linear combination of vectors in R. We saw 2 of them, but there's only one way to write Y as a linear combination of vectors in P. Okay, and it's this idea of casting out the extra vectors and retaining a linearly independent set that gives us this unique linear combination. All right, folks, that's it for this discussion of linear dependence and span. Hope you have a great day, and we'll see you next time. Bye-bye.